Vienna BioCenter Climate Lecture Series. I'm very excited about today's talks. We are dealing with a very important topic. We will talk about greenhouse gases and CO2 emissions, and we're gonna tackle this from two very different angles. But first, before getting to the speakers and to the talks, I would just briefly like to introduce us as a climate group here at Vienna BioCenter. So of course we are concerned about climate change, but also we believe that it is possible to change and to do something for it. And one of the means we envision is to indeed organize lectures, such as the one from today, but also we are very much committed in doing also practical things here at the campus, such as measuring the impact, the footprint, for instance, of the institutes, and also measuring waste production. And if you want to get in contact with us, you have the email, and we're always open to suggestions and feedback. And I would like to introduce briefly the two speakers. First of all, we have Bruce Vaughn from the University of Colorado. I just briefly introduced the speaker. So Bruce is a research associate and fellow at the Institute of Arctic and Alpine Research, the University of Colorado. And he also manages the INSTAR Stable Isotope Lab, where he studies biogeochemical processes that control environmental change on human timescales. And also Bruce is associate with the Arctic Arts Project. And I strongly recommend everyone to visit the blog after the talks because there's very inspiring material. Right after we have Anthony Patt, and is joining from teaching, so will be maybe coming a little bit later. But I want to nonetheless read his CV, which is very interesting, completely different. He is trained as an architect and landscape designer. And from 2000 to 2006, he worked at Boston University together with the Boston Institute for Climate Impact Research. From 2016 to 2013, he headed the Decisions and Governance Research Group at the International Institute for Applied Systems Analysis in Luxembourg, here in Austria. And finally, in 2013, he became an ETH professor on climate protection and adaptation. And also, I think it's very interesting, he's a lead author of the chapter on risk and uncertainty for the IPCC, so the Intergovernmental Panel on Climate Change. So very excited about both speakers and very much looking forward. I just want to quickly remind you the rules of the meeting. So for now, everyone is muted, but as soon as Bruce is done with the first talk, we will open the first question and answer session. You can either raise your hand and we will unmute you. Otherwise, you can just write the question in the chat and I will read it directly to the speaker. So Bruce, can you hear me?
Yes, Luca.
Perfect. Let me stop sharing my screen. Aha, perfect. Welcome. Good morning. You should be able to share your screen.
How's that? Can you see it okay?
Yes, looks great. Please, okay. Bruce.
Great.
Thank you.
Good afternoon, everyone. Thank you for having me, Luca. I really appreciate the opportunity. And I just want to point out one benefit to the COVID crisis. It's made us all more comfortable with the Zoom platform and is allowed, I think, in many ways for exchange between groups around the world, more so than we have in the past. So it's made it easier for groups to get together like this. So thank you for this opportunity. Today, I'm going to give you a view from sort of the trenches. I'm just a field scientist that's part of this whole process, and I have a slight disclaimer to issue. I had a recent knee injury, and before I can get surgery, I'm on pain meds to mitigate the situation. So if I break out in absolute gibberish or grimace or something like that, I'm just going to blame it on the meds. So there's my disclaimer. So anyway, today, this talk could actually be boiled down to three things that if you had to leave right now, you'd get it. With regard to the climate crisis, it's real, it's happening, and it's us. And I realize that I'm kind of preaching the choir here. You people get it, but I also realize that we have a diverse group of people. Some of the people are experts in this exact field. Others maybe doing their science in other fields. So hopefully we'll have something for each group today. And so I don't do this in a vacuum. It takes a village. This is our group at the University of Colorado at the InStar Stable Isotope Lab. And this is just sort of some graphical representation of the kinds of work we're currently involved with. But today I'm just going to focus on these two areas, talking about polar ice cores and greenhouse gases and how they're really important to the climate crisis and our understanding of it. We also work in looking at fugitive emissions of methane and the carbon cycle, as well as measuring new ways to measure the water vapor in the atmosphere. So there are plenty of examples surrounding us today of how the climate crisis is accelerating. I live in the Rocky Mountain West in Colorado, and for us, it's been a horrendous wildfire season. My colleague, Michael Kodas, just recently published this book about the changing nature of fire behavior. We're seeing fire behavior like we have never experienced before. So we can also look at sea ice, and this is a picture in the top of sea ice conditions recently in the Northern Hemisphere and Antarctica in the Southern Hemisphere at the bottom. But what you'll notice, I'll draw your attention to, is Antarctica is pretty much behaving as its mean sea ice extent has been over the last 20 years or so. The gray areas are the median range from 1981 to 2010. And in blue, you can see the 2020 curve. We're not that far off. Very different picture of the Northern Hemisphere, as many of you know, I'm sure. The blue line up here shows a radical departure from the 20-year mean. So we're losing sea ice. And why is that important? The sea ice is kind of, I think of it as like the Earth's sombrero. With its albedo, it can reflect a lot of energy back into space. Without it, the darker ocean absorbs more energy. It goes into the climate system and maybe doesn't directly affect the air temperature, but is actually transferring that heat in the ocean, perturbing the climate system further. So it's actually caught the attention of people, a British teenage activist who wanted to make a point about the sea ice and has gone out and made statements like this. But it's also affecting the ice sheets. Here is the Greenland melt extent 2020, shown here in red through the end of October, November there. And you can see that we're well outside the mean value from 1981 to 2010 again. And this data is collected by the Danish Met Office. And having gone to Greenland since 1988, I personally witnessed a lot of changes that astonished me today. When I go there in the spring, temperatures of -40 are quite common. And the last time I was there, we had temperatures in June that went above freezing. So it's radical change. So a bit of a lag here. There we go. So it's not just the ice sheets in the polar regions, but it's also coming down into temperate glaciers. Here's an image of Columbia Glacier, Alaska. It is a tidewater glacier, so it has a little more complex dynamics, but the right-hand picture is from 1985. That actually is a picture of me standing on a serac from the air. And in 2009, the upper left, you'll see what Columbia Glacier looked like there. It's about 65 kilometers long. And in 2015, it's fully retreated back. You can see the height of the glacier on the trim line in the picture there compared to the Empire State Building. And that location where I was standing in 1985 is right in the middle of the fjord there now. And just a couple summers ago, I was able to paddle on the water where I once stood. So I've spent my whole career kind of dancing around ice cores and glaciers. And I love this quote by Lauren Isley: "If there's magic on this planet, it is surely contained in water." And I couldn't believe that more strongly today. And it is one of the things that we use, one of the tools we use to explore paleothermometry in polar ice cores. So for some of you, you may already be initiated in the world of stable isotopes. For those who are not, I'm going to give you through a one-slide introduction to water molecule stable isotopes and how they work. Basically, it just has, we have oxygen 16 and 18. The 18, of course, has 2 more neutrons, so it's slightly heavier. And we're going to use stable isotopes today in ice cores and greenhouse gases. With ice cores, I hope to impart to you how we derive the paleotemperature records, so you might have more faith and understanding in those records and have a sense of how good are they and what they tell us. And with greenhouse gases, they're also a tracer. And you can think of isotopes as indicators, integrators, recorders, and tracers. So in the atmosphere, it's very much a tracer. In an ice core, it's very much a recorder of Earth's climate history. So most of the water vapor in our atmosphere, as you know, comes from the ocean at low latitudes. Water vapor escaping the ocean is more or less in equilibrium, with some caveats there, with the ocean water. It goes into a cloud. And what happens in the cloud, I like to say, doesn't stay in the cloud. The molecular and physical properties have impact on the precipitation coming from that cloud. Due to the kinetics, the heavier molecules will condense first, and they'll come out of the cloud. So as that cloud moves over continental land masses or towards the polar regions, we have an isotopically lighter and lighter cloud, and that is correlated with temperature. And what does that mean for us practically? Here's a map of the United States showing the mean values isotopically of precipitation in 018 space. So it's basically a contour map that more or less correlates with elevation. So here in Colorado, where we are at higher altitude, we see isotopically lighter precipitation. So you might think of this as an isoscape. What can we do with this? We can, for example, if you were trying to sell me an orange from Florida that actually was grown in California, we could use stable isotopes to distinguish that. It's used in food authenticity, maple syrup, olive oil, drugs, marijuana. As many of you may know, some of the people who ran the Tour de France who got busted for doping, stable isotopes played a role in distinguishing the carbon isotopes of the steroids as different from what they would produce in their bodies. So that's what I love about stable isotopes. It's a tool in a toolbox for many different disciplines. Okay, so let's take that water molecule that's evaporated from the ocean and we pull it. In this case, we're pulling it over Antarctica, and we see a relationship between 018 and temperature, this defined by this curve. This relationship was really teased out by Willie Gansgaard in the 60s in his sort of landmark paper, the isotope precipitation in 1964. And it's on his shoulders that we stand for using paleo temperature records and ice cores through stable isotopes. I'm having trouble advancing, but there we go. So I want to walk you through a little bit of how we obtain ice cores. Oh my goodness. That's not good. I apologize for the unstable platform. Let's try this again. Here's a picture of an ice core drill in Greenland, and it's at this E-script site up here. These red dots represent other ice cores that have been taken over the years. Most of them are with sort of an international collaboration. The earliest one was Camp Century, and then many of these have been European efforts. North Grip, Neem, GISP, and GRIP were US and European collaboration. But here you can see a spinning drill. It's on a cable. We go about 3 meters at a time, and so the ice sheet is in its thickest place about 3,000 meters thick. So it takes several seasons of drilling to obtain an ice core. That's the E-script site. How do we get there? We, on the graces of the 109th Air National Guard, these are ski-equipped C-130s that take us to the ice sheet. Once there, traverses are accomplished with snow track vehicles like this. It's heavy car camping, a lot of cargo. This is a picture of the E-script camp, a drone image. You can see some of the vehicles there. These are garages. The black geodesic dome is a place where we have a galley some workspace, and it's where people take our meals. And pretty much all the ice core work is underneath the ice. You can see over here, there's a slight perturbation in the surface. That is a ramp going down to a whole subterranean world that is where the drill lives and where we do our science. So these trenches below are created with a snowblower, the mother of all snowblowers here. And then they're filled with a balloon. Here you can see our field leader, Jens Petter Steffensen, and he is standing in front of a balloon that's been inflated. That same snowblower then blows snow back in on top of the balloon. It's allowed to sinter for several days, and then the balloon is deflated, and voila, you have a subterranean trench you could drive a snowcat over. And why they did that to test this, I don't know, but it can be done. So what we're trying to discern through our ice core is to go back through the layers of this sort of climate history book. Here you can see someone standing in front of a snow pit that's been dug, and it's probably a couple meters high. On the back of this wall is very thin. There's sunlight being allowed to penetrate the wall to kind of illuminate it like a stained glass window. And about a year's precipitation is shown there. So you could see if there were melt freeze events, which are very few, you could see them, but different storm events show up. So we're basically going back through history. When we bring the ice core up, you could see that sometimes there's dust layers illuminated, and it is a cottage industry for any number of disciplines to do their science on this ice core. People look at volcanics, chemistry, physical properties, and we look at the stable isotopes. How we currently do this is a stick of ice I'm shown here in my hands. It's fed into this little device here, which is called a sort of continuous flow melter. This little hot plate down here is kept warm, and the stick of ice on top just slowly melts. We track the rate at which it melts with a laser distance device. The effluent coming from that is sucked into the little cabin to your right, and we are able to produce the highest resolution ice core records. When I was a younger man, we would analyze ice cores by cutting them up on a bandsaw into little bits and discrete samples. Nowadays, with this continuous flow method, we get a much greater record. So at a meter, 20 years ago, I would get maybe 25 samples. Now I get about 2,400 data points per meter. So it's opened up a whole new window of being able to look at climate from a high resolution perspective. This is what's in the side here. I won't go into great detail. Perhaps most important is the coffee here, which makes it all work. This is basically where the water comes in from the melter. It's turned into a vapor here, and we use cavity ring down laser spectroscopy to measure the stable isotopes of oxygen and hydrogen in these boxes, and the rest is just temperature control. So what do we get? Here is the record from eScript thus far. This is up to date as of a couple weeks ago. The different colors refer to different dating methods were used, but this is about 6 million data points here that you see. And I won't go into detail, but back probably certainly through the red points here, we can actually see summer and winter values in the stable isotope record. It's that good. It's as if you were standing in the ice sheet with a thermometer writing down the temperature every year. And so what this allows us to see is understanding climate of the past in hopes that it may inform our understanding of climate in the future as a result of the perturbations to the greenhouse gases, which we'll get into shortly. So many of you have seen plots like this, CO2 in the top, the temperature in red, and then the sea level at the bottom. You'll notice instantly the correlations between them all. The Eemian period represents a period that's most closely aligned with some of the warming we're seeing today. This little area here, the Holocene, is where agriculture developed over the last 10,000 years. Extremely stable part of climate that we were fortunate enough to be living in. I should point out that, as many of you know, that we're well above 400 ppm, and in the past we never got much more, over 280 parts per million for CO2. So these are the correlations that keep us up at night. It's a large part of why we're there. So I promised some pretty pictures, and these are just a few that Carrie Copping from the Arctic Arts Project has helped illustrate, and they do a wonderful job. If you haven't seen their their site at explaining a lot of the passion of why we're doing what we're doing. So that is a segue into the stable isotopes of greenhouse gases that I wanted to touch on here. We are partnering with the NOAA Climate Diagnostics Lab in Boulder. We measure flasks of air from these sites all over the world. Every couple of weeks, they come back to Boulder and they're measured for how much CO2, methane, and a whole host of compounds that are greenhouse gases or chlorofluorocarbons. We measure the stable isotopes in them for NOAA. And here you can see the what I call a flying carpet diagram. This is CO2 going into the future here from 2008 to 2018. We have latitude, North Pole is on the left and South Pole here, and the CO2 concentration is vertical axis. What you see from this is that most of the action is in the Northern Hemisphere. That's where most of the vegetation is and most of the people are. The South Pole here, you can see the interannual variability, but also a steady rise in the CO2 concentration, even at the South Pole. Here are plots from 4 different sites, starting in the north at Barrow, Alaska, Mauna Loa in Hawaii, American Samoa, and South Pole. And what you'll notice is that there's a much greater amplitude in Barrow in the Northern Hemisphere, and this is due to the interaction of plants absorbing CO2 in the summer when they're photosynthesizing, drawing down the CO2 in the summer, and in the winter we're burning more fossil fuels and the CO2 level goes up. The signal is sort of dampened as you move further south. So part of the reason it's driving that is the plants I mentioned, mostly in the Northern Hemisphere. But there's another feature that we exploit with stable isotopes, and that is the fact that most plants prefer carbon-12 CO2 over carbon-13. So when you and I are burning our fuel in our automobiles, we're burning predominantly C12 CO2 as the effluent. And as we put more and more of that into the atmosphere, the concentration of C13 in the atmosphere is decreasing over time. So this is one of the reasons why we know it's real, it's happening, it's us. This is basically our fingerprint on the atmosphere of C13 as the mixing in the atmosphere goes down over time. So I know we have other speakers today, and so I want to just wrap up by saying this is probably the most important challenge I think we as a species face. And I think we should no longer refer to it as climate change, but really climate crisis. And we're going to have to change the way we work, change the way we produce energy, the way we move ourselves around. We have a lot to do. And a lot of that is our carbon footprint. And I would like to leave people with a little bit more positive note. I would like to direct you to this website, SEEK, which is the Sustainability for Energy and Environment Complex at Colorado. On this website, you can see if you're concerned about actions you might engage in to help make a difference, whether they're in policy, energy, transportation, products, food, justice, or resilience. There are concrete examples of how you yourself can make a difference. And with that, I'll leave it there. And if there's time for questions, we'll take them. If not, we can deal with them later. That's all I have for you.
Thank you so much, Bruce. Great talk. It's also great to see the logistics to do such measurements. It's really interesting. I think we do have, say, 5 minutes for questions. So again, if people want to ask the questions in the chat, I can read them directly to Bruce, or you can also raise your hand and we can unmute you. And maybe I can start. Very naive question, but I heard several times about this CO2 trap technology and this, yeah. Is it, how much do you believe in that? Is it a possibility to decrease the CO2
for carbon sequestration?
Yeah.
It's part of the equation, and I think we should be looking at every tool we have. And our next speaker may have more to say about that than I do. By and large, I remain a skeptic for any what I would call geoengineering approach to solving our problems. That has typically been an approach we've used in the past to tackle many of our challenges. It could help, but I think if we've learned anything over the last, I don't know, few centuries about our attempts to manage our environment, we have a track record that's woefully inadequate. Channeling, whether you're channeling rivers or intervening in wildlife populations, we don't have a great track record. Could they work? Yeah, maybe. And I think there's people that know far more about it than I. They could weigh in on the carbon sequestration, but I think we have to have a very diverse portfolio of dealing with this from a lot of different angles.
Yeah, okay, thank you. Yeah, Robin wrote in the chat that yes, after this talk, if we can circulate the website you just showed, and so yeah, we will make. Okay, perfect. It's already in the chat. So please, everyone, have a look at it, and we also will share it after the talk via email. And is there more questions? Otherwise, we will have another session after the second speaker. So.
Okay.
Get ready for more questions, and Anthony should be here.
I am here.
Okay, hi.
Hi.
Welcome.
Hi, thanks. So should I jump right in then?
Please, go ahead.
Good.
If you could
Okay,
share
I can share my screen. I am going to do a so-called advanced screen sharing, which for me somehow works better. And you should see my picture in the lower right-hand corner in a moment, if you're using the most recent version of Zoom. And if you're not, I don't know, am I there now?
Ah, yes, I can see you. Ah, that's fancy. Okay.
I'm going to make myself really small so I don't get in the way of the text, but somehow this works better for me. Okay, so somehow the title of my talk is Yes, We Can Get to Zero CO2 Emissions. I completely agree with the last speaker, with Bruce, that we need to solve this problem, and really to solve it, we need to get to zero CO2 emissions. And I'm going to talk with 27 slides and 20 minutes on the technical, economic, political, and personal dimensions of decarbonization, which is probably impossible to do in 20 minutes. And I'll raise more questions than I ask, and there won't be time to answer them unless I'm completely confusing you. And if you have questions after today, feel free to email me and ask. Okay. So I'm zooming to you from Zurich to Vienna. I guess the previous speaker, those look like the Flatirons in Colorado. So I'm not there. I'm in snowy Zurich today. Okay, I'm going to dive right in with the technical side. What do we actually need to get to zero emissions? I mean, I think for most of us, it seems like an incredibly complicated question, an incredibly complicated problem. But if you start to break it down, it gets a little bit simpler. And the first way to break it down is to say, well, where's the energy coming from? If you look at the world, which is this left-hand graph, it's mostly fossil energy, but there's a lot of agricultural, forestry, and land use emissions, and a lot of other industrial greenhouse gases, which are the non-CO2 gases from industry, like F-gases and so on, but also stuff from cement production, steel production, and so on. If you look at the OECD countries, and we all live in OECD countries, I guess, that's Western Europe and North America, the rich countries, it's mostly fossil energy, and there's very little agriculture, forestry, and land use. The agricultural, forestry, and land use emissions are mostly coming from tropical countries where there's still deforestation going on. So let's call it 80 to 90% a fossil energy problem. And for us, another 10 to 20% other industry stuff. So let's then break that down even further. And if we look at the energy sector, which is where I do most of my work, this equation is incredibly valuable. It's called the Kaya identity. It's actually an identity, not an equation. The units simply cancel out. It's a way of decomposing our CO2 emissions into the various factors that cause them. And so it's our CO2 emissions per year, and this is in the units of gigatons, is equal to the number of people on the planet times how much money each person gets to spend a year, times the energy intensity of our economy, which is how much energy we need to generate $1 or €1 of value in society, times the carbon intensity of our energy, which is how much CO2 comes out of each of those units of energy. And the clear thing is that if we want to get to zero emissions, and we do want to get to zero emissions, we need to get to zero emissions if we're going to stop climate change below really catastrophic levels, we need to get to zero emissions. So the left-hand side of the equation is zero. We need to get to zero, which means there's no way around it. One of the elements on the right-hand side needs to get to zero. And it's also, I find this actually a liberating thing because there's only one of them that can get to zero, and that's the right-hand unit, the carbon intensity. And I find it liberating because if the carbon intensity does get to zero, and we know we need to get it to zero very quickly, then that actually buys us a little bit of room for maneuvering on the other three. We don't necessarily, for the climate anyway, need to get to fewer people, less affluence, or less overall energy use. We're actually probably going to get to less energy use. Our efficiency is always improving, but our energy intensity is always improving. But it's really in the carbon intensity that we need to make the biggest difference, and that has to get to zero. And that simply means getting the fossil fuel out of our system, 100%. And then it's useful to break down where we're actually using the energy and where fossil fuel is mostly used and where other forms of energy are also used. One way of breaking the energy system down, and this is a rough breakdown for OECD countries. Austria is a little bit different. Switzerland's a little bit different. We have a lot of hydropower, so that makes it quite a bit different. But for wealthy countries in general, we use the most of our energy for heat, followed by mobility, and then finally power generation. And the power, of course, we use for all sorts of things like the computer screens that you're probably staring at right now. And it's in power generation that we make the most strides away from using fossil fuels with renewables, and most of that is hydropower, but there are new renewables coming online. And the ones where we really have the room to develop more are with solar and wind. And of course, we have a lot of nuclear power. That's probably not going anywhere fast because there's a lot of public opposition to it. Then in the heat area, we have a fair amount of renewables. Most of that is biomass combustion. And on the mobility side, we also have some renewables. That's going to be biofuels partly, and also electricity-based mobility like the train system, which in countries like Austria and Switzerland is based on hydropower. So the absolute requirement is to get rid of the gray from this picture, right? And to get rid of the gray, pretty much everyone agrees you need to do three things. First, you need to make all the electricity renewable, and primarily that's from solar and wind, simply because the available capacity for solar and wind is far more than we actually will ever need. Second, you use electricity for as much of mobility and heat as possible. And third, for whatever's left, like aviation, where electrification isn't really possible, use solar energy to convert carbon dioxide, which you capture out of the air, and water into liquid hydrocarbons, which is some molecule with carbon and hydrogen in it. And you can do this. There are the technologies out there to do it. It's very expensive right now. And ultimately, if you're going to do those three things, we need 5 sets of technologies. We need reliable renewable electricity generation, primarily solar and wind, with batteries and balancing to make it reliable. And the big questions, I think, really are, can we get enough of it? And the answer is yes. And can it be reliable? And the answer is yes. Can we get enough of it? Well, if we were to do it stupidly, we wouldn't get enough of it. But if we do it reasonably intelligent, we probably can. This left-hand picture shows how much land area there is on the planet, 149 million square kilometers. The largest share of this is being used for food production, 49 million square kilometers. If we got all of the energy that we're projecting to use in 2030, which is a little more than we're using now, and we got all of it from photovoltaic panels, we would have to cover about 500,000 square kilometers of land area with photovoltaic, which is, I suppose it's about 6 times the area of Austria. So it's a lot of land, but when you actually look at the amount of land, it's a lot less than we use for other things like agriculture. If we were to do a lot of windmills, of course, that's synergistic with that agriculture. But if we were to put it in desert areas, there's more than enough land. We're talking about a small fraction of the Sahara Desert. And of course, we can put an awful lot of it on our rooftops. In countries like Austria and Switzerland, we probably could get most of what we need from our rooftop area. It's a lot of glass you're talking about for these things, but it's actually not that much compared to the rest of industrial society. So we can get enough of it. Can it be reliable? And the answer again is yes. You either do it with batteries or you do it with transmission lines. Batteries are expensive, but easy politically, whereas transmission lines are the opposite. They're actually really cheap to build. But if you were to build a network like this on the right with huge transmission capacity, it would take a lot of international cooperation to get that to happen across the bounds of different continents. So it's something which is possible. The easy solution politically is more expensive. The cheap solution is a bit more complicated. It seems, though, that as the costs for all of these things fall, that the political solutions seem to work out better and better. Okay, next thing we need are electric vehicles for ground mobility. That's cars, trucks, tractors. I drive one of these cars on the left. It's a wonderful car. Of course, even better is I ride a bicycle to work, so that uses, well, no electricity, but and of course public transportation is there, and that's better than driving a car. But if you're going to drive a car, you can now drive an electric car, which works just as well, if not better, than a gasoline car. There's a lot of negative publicity around electric cars right now. From my reading of it, most of the negative publicity is wrong. If you actually do the life cycle analyses of electric cars, they're actually fine. They're better overall in every way in their environmental consequences than sticking with gasoline cars. Electric cars, of course, they're part of how you get to a zero carbon automobile sector. The other stuff like tractors, they're coming. They're actually coming. This is the latest model John Deere electric tractor. The major tractor builders are building these things, and you're seeing this across all sorts of construction equipment around the world. We're making the movement towards electrifying mobility because batteries are advancing so quickly. They're becoming cheaper, they're lasting much longer, they're requiring fewer resources. So this is coming along. The third thing we need are electric devices for space heating and process heat. This is primarily heat pumps where the temperature gradient you have to cover isn't that much. And for other things, you just use simple electric heating devices. This is not a problem. We have these technologies. The next is green hydrogen and hydrocarbons, power to X, for fuels, steel, and chemical feedstocks. So the hydrogen is pretty easy. You just use renewable energy like we see on the left here to split water. And you use renewable electricity to split water, and then you can use that. You can either use the hydrogen later to reproduce electricity, or you can use it, for example, to turn iron ore to reduce iron, and which you need in the steel industry. You can also, so the hydrogen is not so hard. The trickier thing is the hydrocarbons, because for that you need to take CO2 out of the air and use the carbon in that, split the carbon dioxide as well as splitting the water to create the precursors for more complex hydrocarbon chains. The technologies exist. They're really right now starting to come out of the lab and enter the market. This picture on the right is the first pilot facility demonstration project, which shows a self-contained unit that creates kerosene that you can use in an airplane out of sunlight and air. It's the first installation. It went online 3 years ago on top of a lab, actually in Zurich. It only produces, a few liters of the stuff every month. So it's not commercial scale, but the next generation is going online right now in Spain. It's moving incredibly fast. So these things are happening. We have the technologies. They need to move out of the lab into the market. The final thing we need is carbon capture and storage for cement, residual emissions, and negative emissions. And I know the previous speaker was skeptical. I think it's important to separate geoengineering into two very different things that we can do. One is taking CO2 out of the air and doing stuff with it. And I actually wouldn't call that geoengineering. That's just sort of carbon management. And the other is solar radiation management, which means stuff like pumping sulfate aerosols into the stratosphere to block incoming solar radiation, which I think is incredibly dangerous. Anyway, we need carbon capture. We need it Because cement is a major source of emissions, and the only real way to get the carbon out of cement production, the chemical reaction carbon, because when you're making it, it goes through chemical reactions which freeze CO2, just like with reducing iron to steel, you get CO2 coming out. With cement, the only good way to do it is with carbon capture. And all of the scenarios that we show, well, and you need the CO2 for the hydrocarbons, the power to fuel hydrocarbons. You also need it for some of the residual emissions to balance out the residual emissions like we're going to have probably from agriculture, and to get negative emissions. All of the IPCC scenarios show us with a lot of negative emissions being required if we're going to stay under 1.5 degrees warming. The amount of negative emissions we want are vastly more than we can cover with afforestation projects or with using bioenergy coupled with CCS. We're going to need to do direct air capture with these machines like I show on the left, and then sticking the stuff underground. All of the studies that have been done so far have shown it to work. And the most exciting, I think, is this picture on the right, which is a demonstration facility in Iceland, where they pump water with CO2 mixed into it into the basaltic lava rock, and it reacts, it completely mineralizes within a matter of weeks and completely locks it up permanently. And there's more than enough of these kinds of deposits around the world to be sequestering this stuff on a gigaton scale. What about the economics of it? The economics, this is where stuff is exciting because it's really, really changed in the last decade. The first three of the things we need have come so fast, so much faster than we expected, that they are now already the least cost things. So reliable renewable electricity generation is in more and more places around the world the least cost way of getting electricity. And less reliable electricity generation with a solar photovoltaic without a battery is almost everywhere now the least expensive, either that or a windmill. But even to make it reliable, adding in the cost of storage in more and more places, it's become the least expensive. And Colorado, for example, is one of those places. Electric everything for ground mobility is becoming the cheapest. It's already the case with cars that an electric car, the lifetime ownership costs of an electric car are less than a gasoline or diesel car. We're going to be reaching the point within about a year and a half where the initial purchase price of an electric car will be at or below that of a gasoline car. The actual cost of the energy is much, much less because you can utilize cheap wind and solar power, which is much cheaper than gasoline. And for example, the energy return on investment, you need to put far less energy into creating solar power than you do to getting oil out of the ground and moving it to where you need it. So we're going in the right direction. Electric heating devices are already usually the cheapest option. It's a little more problematic with green hydrogen and hydrocarbon. These are right now quite expensive. They cost, let's say, 3 or 4 times as much as fossil equivalent fuels. But they should become cheap. And the estimates are that they might become least cost, but if not least cost, then almost least cost. There won't be a huge difference. Carbon capture and storage is always going to be more expensive. It's always, a power plant with carbon capture and storage is always going to be more expensive than a power plant without it. And if we're using negative emissions, those negative emissions are always going to cost us something on top of whatever we are already having. A critical question is how much are we talking about? And it seems like a lot, but it's actually, I think it's all possible. So let's look at cement, for example. If you were to add carbon capture and storage, CCS, to cement production, it would add about 5% to the cost of the concrete that you're making. And with the concrete costs on a lot of construction projects being like half of the total cost, it's going to add a couple percent to the cost of building stuff, but it's not prohibitive. What about, take, for example, the non-CO2 flight emissions? When you fly in an airplane, of course, you're emitting CO2, but you're also putting other greenhouse gases into the air. And let's say we did negative emissions to compensate for those. Well, this kind of offsetting, it would add, if you run the numbers based on where we think the costs of CCS are going, the CCS offsetting would add about 25 euros to the price of a Vienna to London flight, which is something, but it's not prohibitive. What about negative emissions? Well, we're projecting we're going to need something like 10 gigatons a year of negative emissions. And at that rate, we're talking about $1 trillion per year globally that we would need to get to a 1.5 degree scenario, which is on, it's the same order of magnitude as what we spend on defense. So that, I think, is that's the hard point. In total, probably if you add up all these three costs, all the costs of carbon capture storage when we're needed, probably the extra costs are actually about the same or less than the savings we're going to get on items 1, 2, and 3. So, we can run our economy as we do now, doing all these 5 things, and we're not going to notice a huge difference. But at the same time, this number 5 is going to be a challenging thing on its own economically. What about the political side? Well, the political side, I want to start now with the non-energy emissions. First of all, I want to say we have no clue how to reduce non-CO2 emissions from agriculture. And those are probably going to be our residual emissions. This graph here shows what's happened to emissions from the agriculture, forestry, and land use sectors over the last 40 years. What we can see is that the agriculture component of those have been basically staying the same, rising just a little bit. And the land use peaked about 20 years ago and then have been falling. So we've basically done nothing on the policies for the agriculture sector, and we just don't know what to do. Maybe we'll figure that out. When it comes to land use, the fact is that almost all countries have realized it's in their own national interests to eliminate deforestation. And when we've helped them realize what's in their national interest, they've succeeded. For a while in Brazil, for example, we did that. This graph here shows deforestation in Brazil over a 10-year period from 2002 to 2012, and it saw drastically falling emissions. Most of that was from large-scale clearings, a decline in large-scale clearings. And the key factors were rural to urban migration and formalizing and enforcing the land use rights. Anyway, it works. We know how to do this. It's also the case in Brazil that the Bolsonaro government has reversed this trend. I would say the fewer populist authoritarian leaders, the better. Unfortunately, there's about to be one fewer of those in the world. So we have solutions, and part of the solution is making sure we elect the right people. Okay, this is kind of controversial, but it's really my take, and I think more and more people are starting to realize it. Carbon taxes don't work very well. Why don't they work well politically? First, they force individuals to bear the cost to future generations of their own actions today, and few of us like doing that. And that's a political problem. It's hard to get carbon taxes introduced at rates that are high enough to make any difference. And second, there's a behavioral problem. They work when we invest in new and untested technologies based on potential future cost savings. And the fact is, few of us do that. It's just too risky. And carbon taxes don't really address that. I'd be happy to talk more about this. It's a big theme of mine. We see that they don't actually work that well. And fortunately, though, we're seeing that other things do work. And what works is a sequence of policies that start with money for research and development, move into technology support, and then end up with technology standards. A really good example of this is what's happened in Norway. So Norway has gotten to be the absolute leader in electric cars. Starting around 2009, you saw new options entering the market as a result of battery research programs in Germany, Japan, and the United States, much of which were a response to the recession. They were part of the financial rescue package back from 2008. These started to lead to new cars actually entering the market. In 2012, Norway started supporting electric vehicles with a mix of financial incentives and infrastructure like charging, and their market really started growing. By the end of 2016, they were able to start phasing out the incentives. They'd reached their goal of 50,000 electric vehicle sales a year, and they were able to announce a prohibition on internal combustion engine vehicles being sold, new ones being sold, that would start in 2025. And they were able to do that because the support mechanisms for electric cars had convinced people that these things worked. Anyway, since then, they've been growing since, and this year they're on track to a 67% market share, for vehicles with a plug, which is on track towards 100% in 2025, which is what they need to be at when they phase out the sale of new electric vehicles. What about negative emissions? This is tricky. I don't have any easy solutions, and nobody else does either. And we better start figuring it out soon, because it's something that, that we're going to have to figure out. I would say, why do today what you can put off to tomorrow? And this is a little bit ironic, because in Switzerland, actually, we're starting tomorrow to think about it. I'm part of the first set of meetings looking at this between my university, which is the National Technological University, and the government, thinking about policy frameworks for negative emissions and how we're going to get those going. And what about the personal? This is where I wrap up. What can we as individuals do, or in your case, as a university laboratory, do to get our emissions down? And again, I want to return to the 5 things, and I've changed them around a little bit to match sort of the personal choices we can make. The first is renewable electricity, and this is pretty easy. You can, people can build your own PV, but you don't even need to do that. You just need to buy 100% renewable power from the grid, and that's available everywhere. You can, and when you do so, you increase the financial incentives for more of this to get built, which is the big challenge, simply building enough. The second is you can move towards electric ground mobility, and this isn't particularly hard either. So for your private car, you can do that, but universities and institutions can do this as well. My university we run a bus system between our 2 campuses. They just converted it to an completely electrified bus system. All our delivery vehicles on campus are now electric. These have just gotten good enough that we can do this across the board as institutions. What about electric space and process heat? This is easy as well. The next time you replace your heating systems, you replace them with these, and you can do it, and it pays over the long run. This is getting trickier, getting green hydrogen and hydrocarbons going. And this, of course, is what we need if we're going to fly fossil free. This is just now really starting to happen. When it comes to making synthetic hydrocarbons, non-fossil hydrocarbons, the first commercial scale facility was announced in July this year. It's a project in Norway, Norsk e-Fuel, which is getting all of its electricity from a wind farm, offshore wind farm. It's going to be the first commercial scale facility actually supplying sustainable, non-biomass based fuels to the airline industry in Europe. The first demonstration plant for fossil-free steel was just completed and is just starting to be used. So we're moving there, but it's going to take time. And as individuals, there's not much we can do because there just isn't much of this available. We need some patience, and we need the policy frameworks there to bring these things further along. And what about gray emissions and all this stuff? So all of the energy that's embedded in what we buy and use, how can we get rid of that? And the fact is, as individuals, there's basically nothing we can do other than be patient. So on the one hand, we need to let governments around the world actually do their own job of getting their own energy systems down to zero. And as they do that, of course, the stuff made in those countries will move. This is what the Paris Agreement is there for. It's there to help countries get this and to give them an incentive to set zero emission targets. The most recent one has been China, which now has a target for 2060, which is incredibly good news. The Paris Agreement is also there to help them with support for finance and policy development. And then, of course, there's stuff happening on the private sector side, such as the RE100 Alliance, which is an alliance of businesses which have committed to getting to 100% renewable energy supply chains fairly quickly. These things have to get going. There's not a whole lot we can do as individuals. So to summarize it all up, technical, we need 5 things and we have them. Economic, in total, they will save us money, although the savings will be in some places and other places will cost us something. Political, there is a political roadmap for most of this, and it's fairly new, but it's very good news. And then personally, there's a lot we can do individually and some stuff where we need to wait for countries and companies to take the lead. And then I want to finish with one final slide. If it looks this good, why aren't we doing anything? And the answer is, actually, we're doing a lot, and we're doing it at an accelerating pace. I can say in my working group of the IPCC on mitigation, our message is different now than it has been in the past. We see hope and we see a light at the end of the tunnel. Outside of recession, sectoral emissions fall hand in hand with the diffusion of low carbon technologies. And these things take time. Diffusion curves, and these curves in the background, those are diffusion curves, right? Diffusion curves are logistic, they're not linear. It's the same as population growth curves. It doesn't happen linearly. It starts slowly, it gets big and accelerate, and then it flattens out again as you get towards full market penetration. And the fact is, our job is to bend these curves backwards. And we're doing so, but even so, what we've seen so far has been tremendous on the technology side, and we're only now really seeing where the technologies are coming into market at sufficient scale to displace the fossil fuel that's there. So that's it for me. Thanks.
Amazing. Thank you so much. And yeah, it's really inspiring also to see there's so many things that are likely developing so quickly. And again, I would like to prompt the audience to ask questions. And I actually have one. I have plenty. So, so let's get.
I'm going to read. So I'm reading the chat. Fantastic. Go Norway.
Okay,
Yeah,
please
go Norway.
go.
But it's not just Norway. In Europe, EVs this year are probably going to come in close to 20% market share. It's phenomenal. They're growing so fast. I mean, I think the UK just advanced their deadline for phasing out the sale of gasoline and diesel cars. They had set a target 2 years ago of 2040. They just announced 2 weeks ago they're accelerating it to 2030. It's changing fast. It's fantastic. Norway has one of the biggest amount of non-private funds of money in the world. Now, hold your breath. It's earned mainly the fossil fuels they sold before. So that schizophrenia is very common in these discussions. It absolutely is. Thank you, Anthony. You mentioned that we don't know how to reduce agricultural emissions, but what about measures to reduce meat and dairy consumption? Yeah, I think that's probably something we need. No country has tried to do that. Politically, it's a big puzzle how you can even get anything in there to reduce that, because you hit against the farm lobby. It seems like enteric fermentation makes up a big chunk. That's absolutely right. Thanks for a great. If the carbon capture is rather complicated, wouldn't replanting trees solve the problem? Planting and replanting trees is a lot cheaper, and in fact, it's probably free because the other benefits probably outweigh the costs. But if you add up the numbers, it's not enough. You know, it can probably get 10 to 20% of the negative emissions that we need, but it can't get the other 80%. We just don't have enough land. Yeah. Anthony, what's the compromise with the electrical car batteries? To be honest, there aren't that many compromises. You can recite there are local environmental consequences, but they're vastly less than for oil. So we solve a lot of local environmental problems. The batteries are 95% recyclable. We don't actually face resource constraints. They're becoming longer lived. The only downside is that I think driving a car is going to become even cheaper than it is now, and people are going to want to drive them even more, and that's a bad thing for our cities. I guess that's it. I find it very surprising that carbon tax is not working. Could you elaborate a bit more on why? So what we see with carbon taxes is it really leads to efficiency improvements. And efficiency improvements, they respond to this incentive, especially when we're talking about corporate efficiency measures, a little less so with private individuals. The problem is that a lot of the new technologies we need that are zero carbon rather than reduced carbon require different, they often require different infrastructure networks. For example, if you want to have a zero carbon electric power system, you need a lot more power transmission. Otherwise, you end up with too much, you need a lot more power transmission or storage. And the market structure is a bit different. And the problem is that if you simply raise the price of fossil energy, but you don't address the more systemic constraints, investors find it really risky to invest in, because ultimately they might lose money. For example, if you have solar power and there's too much of it in the middle of the day and there's no capacity in the system to store it, you don't know if you can actually take advantage of its low costs, the ability to sell it for low cost. So that you need to address these other things. Now, carbon taxes can be great if they're used also, if you recycle the revenues to finance the other stuff you need. And that's absolutely fine. And so they're really good as a revenue raising tool, but alone they don't overcome what turns out to be the more systemic barriers these problems. I don't put responsibility on the, so thank you for your time. I nevertheless disagree with some points. I do think that putting the responsibility on the individual level, i.e. buying renewable energy, is not the right course. Well, I'll agree. I think, you know, we need government policies that gets this to happen. But if we're looking for things to do as individuals, there is stuff we can do in a few areas, but not in others. I argue that political organizations like Fridays for Future, blah, 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 are crucial in changing the political landscape. I absolutely agree. You mentioned surface for PV like rooftop, but what about road? Are the technologies there? Yeah, I think roads are probably not the best place you want to put them because, first of all, you're driving over them, which shades them, and second, probably making a non-skid solar panel is going to be much more expensive than, and you know, making one that's robust for driving a snowplow over too. I don't know. Phenomenal talk, super interesting. Thanks so much, Paul. Is the fossil industry in a position to counteract the now cheaper renewables by becoming cheaper themselves in some ways? Yeah, they've been doing that, but they haven't been keeping pace. What we have seen, I think what we are going to see fossil fuels become cheaper simply because demand is turning a corner. Certainly demand for coal is already falling. Demand for natural gas and oil are starting to fall as well, and this pushes down the prices. So we have to fight a moving benchmark, but I think we can do it. Got to run to another meeting, Bruce. What if right-wing populists on top of governments become more and more? Well, then we're all screwed. Thanks, Bruce. Amazing talk. And that's okay. There you go. Do you ultimately think that emissions reduction would be fast and effective enough to overcome the nasty effects of many positive feedbacks that are contributing to global warming? Not without negative emissions. And we need them. And that's the next big hurdle that we're only now starting to think about. Okay. Sorry, I talked at an amazingly fast pace.
Fantastic. No, you also my job. Perfect. No, it was great. Yeah. Okay, you had plenty of questions. And as you said, people can reach you, I guess, per mail.
Good.
And I thank everyone for joining us today. I really enjoyed it. It was very, very interesting. And yeah, next climate talk is going to be 12th of January. Helga Baish will talk about social metabolism. And if anyone is interested, please join up. And thank you, Anthony. And also thank you, Bruce. He just left. And I wish everyone a nice evening. Thanks again.
Can I respond to one more question?
Of course, yes.
There's one more question from Jörg to everyone. The CO2 footprint from solar power is far from zero. That's absolutely true. But the thing that we have to do when we think about these footprints is ask whether it can be a part of an energy system that uses no fossil fuels at all. And solar power can. So right now, it does have a CO2 footprint. You need a lot of energy to produce it. It actually has a better energy return on investment than fossil fuels, but of course, it's not zero. But it could be, one can imagine an energy system based on solar and wind, which has no fossil fuels in it. And if there are no fossil fuels in the energy system, then the CO2 footprint of all of the things you are using is zero. If you've also addressed, cement and steel and stuff like that. So to my mind, the critical question is to think about the system we want to get into have in the future and how that all fits together, not what the CO2 footprints are right now. Okay, thanks.
Super. Thanks a lot again.
Good. Bye-bye.
Thank you. Bye-bye.